Bismillahirrahmanirrahim. This is the second part or continuation of the lecture number 37, which is about the carbon dioxide sequestering or carbon sequestration with reference to environmental chemistry. Here is ocean related iron fertilization. Ocean iron fertilization is an example of such a geoengineering technique. Iron fertilization attempts to encourage phytoplankton growth, which removes carbon from the atmosphere for at least a period of time. This technique is controversial due to the limited understanding of its complete process or effects on the marine ecosystem, including side effects and possibly large deviation from the expected behavior. Such effects potentially include release of nitrogen oxide and disrupting of the ocean's nutrient balance. Natural iron fertilization events such as deposition of iron-rich dust into the ocean water can enhance carbon sequestration. Sperm whales act as an agent of iron fertilization when they transport iron from the deep sea or ocean to the surface during preying consumption and defecation. Sperm whales have been shown to increase the level of primary production and carbon export to the deep ocean by depositing iron-rich feces into the surface water of the Southern Ocean. The iron-rich feces causes plankton to grow and take up more carbon from the atmosphere. When the phytoplankton dies, some of it sinks into the deep ocean and takes the atmosphere carbon with it. By reducing the abundance of the sperm whales in the Southern Ocean, whaling has resulted in an extra 200 lakh tons of carbon remaining in the atmosphere each year. Here is urea fertilization. Ian Jones proposes fertilizing the ocean with urea, a nitrogen-rich substance that encourages phytoplankton growth. Australian company Ocean Nourishment Corporation plans to sink hundreds of tons of urea into the ocean to boost carbon dioxide absorbing phytoplankton growth as a way to combat climate change. In 2007, Sydney-based ONC completed an experiment involving 1 ton of nitrogen in the Sulu Sea of the Philippines. Now here is mixing layers. Encouraging various ocean layers to mix can move nutrients and dissolved gases around, offering any view of geoengineering. Mixing may be achieved by placing large vertical pipes in the ocean to pump nutrient-rich water to the surface, triggering blooms of algae, which store carbon when they grow and export carbon when they die. This produces results somewhat similar to iron fertilization. One side effect is the short-term rise in carbon dioxide, which limits its attractiveness. Seaweed. Seaweed grow in shallow and coastal areas and capture significant amount of carbon that can be transported to the deep ocean by oceanic mechanism. Seaweed reaching the deep ocean sequester carbon and prevent it from exchanging with the atmosphere over millennia. In addition, seaweed grow very fast and can theoretically be harvested and processed to generate biomethane via anaerobic digestion to generate electricity via cogeneration or as a replacement for natural gas. One study suggested that if seaweed farms covered 9% of the ocean, they could produce enough biomethane to supply Earth's equivalent demand for fossil fuel energy, remove 53 gigatons of carbon dioxide per year from the atmosphere and sustainably produce 200 kilograms per year of fish per person for 10 billion people. Ideal species for such farming and conversion include Lamina digitata, Fucus staterosa and Saccharina latissima. Here are physical processes which are biomass related. Number 1. Bioenergy with carbon capture and storage. Bioenergy with carbon capture and storage refers to biomass in power stations and boilers that use carbon capture and storage. The carbon sequestered by the biomass would be captured and stored, thus removing carbon dioxide from the atmosphere. Number 2 is the burial. Burying biomass directly mimics the natural processes that created fossil fuels. Now, biochar burial. Biochar is a charcoal created by pyrolysis of biomass waste. The resulting material is added to a landfill or used as a soil improver to create terra preta. Addition of pyrogenic organic carbon, which is known as biochar, is a novel strategy to increase the soil carbon stock for the long term and to mitigate global warming by offsetting the atmospheric carbon up to 9.5 carbon annually. In the soil, the carbon is unavailable for oxidation to carbon dioxide and consequently atmospheric release. According to the Simon Shackley, people are talking more about something in the range of 1 or 2 billion tons a year. Ocean storage. If carbon dioxide was to be injected to the ocean bottom, the pressure would be great enough for carbon dioxide to be in its liquid phase. The idea behind ocean injection would be to have stable, stationary pools of carbon dioxide at the ocean floors. The ocean could potentially hold over 1,000 billion tons of carbon dioxide. However, this avenue of sequestration is not being as active pursued because of concern about the impact on ocean life and concerns about its stability, a biological solution can be growing seaweed that can naturally be exported to the deep ocean, sequestering significant amount of biomass in marine sediment. River mouths bring large quantity of nutrients and that material from upper river to the ocean as a part of the process that eventually produces fossil fuels. Transporting material such as crop waste out to sea and allowing it to sink exploits this idea to increase carbon storage. International regulations on marine dumping may restrict or prevent use of this strategy and technique. Geological sequestration. Geological sequestration refers to the storage of carbon dioxide underground in depleted oil and gas reservoirs, saline formation, or deep unminable coal beds. Once carbon dioxide is captured from a point source, such as a cement factory, it would be compressed to nearly 100 bars so that it would be a supercritical fluid. In this fluid form, the carbon dioxide would be easy to transport via pipeline to the place of storage. The carbon dioxide would then be injected deep underground, typically around 1 kilometer, where it would be stable for hundreds to millions of years. At these storage conditions, the density of supercritical carbon dioxide is about 600 to 800 kg per meter cube. The important parameter in determining a good site for carbon storage are rock porosity, rock permeability, absence of faults or geometry of rock layers. The medium in which the carbon dioxide is to be stored ideally has a high porosity and permeability such as sandstones or limestones. Sandstone can have a permeability range from 1 to 10 to 5 Darcy and can have a porosity as high as nearly equal to 30%. The porous rock must be capped by a layer of low permeability which acts as a seal or cap roll for the carbon dioxide. Shells is an example of a very good carved rock with a permeability of 10 to 5 or 10 to 9 Darcy. Once injected, the carbon dioxide plume will rise via buoyant forces since it is less dense than its. There is a fault planned near the injected zones. There is a possibility the carbon dioxide could migrate along the faults to the surface, leaking into the atmosphere, which would be potentially dangerous to life in the surrounding areas. Another danger related to the carbon dioxide sequestration is induced seismicity. In the injection of carbon dioxide creates pressures that are too high underground Deformation will fracture, causing an earthquake also. While trapped in a rock formation, carbon dioxide can be in supercritical fluid phase or dissolved in groundwater or brine. It can also react with minerals in the geological formation to precipitate of carbonates. Worldwide storage capacity in oil and gas reservoirs is estimated to be 675 to 900 gigatons carbon dioxide, and in unminable coal seams is estimated to be 15 to 200 gigatons of carbon dioxide. Deep saline formation have the largest capacity, which is estimated to be 1,000 to 10,000 gigatons of carbon dioxide. In the United States, there is an estimated 160 gigaton carbon dioxide storage capacity. There are a number of large-scale carbon capture and sequestration projects that have been demonstrated the viability and safety of this method of carbon storage, which are summarized here by the Global CCS Institute. The dominant monitoring technique is imaging, which white weight are generated that propagate through the surface and subsurface. The geological structures can be imaged from the refracted or reflection waves. Chemical processes. An electrocatalysis by a copper complex helps reduce carbon dioxide to oxalic acid. This conversion uses carbon dioxide as a feedstock to generate oxalic acid. Mineral carbonation. Carbon in the form of carbon dioxide can be removed from the atmosphere by chemical processes and stored in stable carbonate minerals. This process is known as carbon sequestration by mineral carbonation or mineral sequestration. The process involves reacting carbon dioxide with abundantly available metal oxide, either magnesium oxide MgO or calcium oxide CaO, to form stable carbonates. These reactions are exothermic and occur naturally. In these reactions, as it is described, calcium oxide reacts with carbon dioxide to form calcium carbonate, and magnesium oxide entrap carbon dioxide as magnesium carbonate. Magnesium silicate reacts with carbon dioxide to form magnesium carbonate and silicon dioxide, whereas a hydroxide mineral reacts with carbon dioxide to form magnesium carbonate, silicon dioxide, and water. These reactions are slightly more favorable at low temperatures. This process occurs naturally over geological time frame and is responsible for much of the Earth's surface limestone. The reaction rate can be made faster, however, by reacting at high temperatures and pressures. Although this method requires some additional energy, alternatively, the mineral could be milled to increase its surface area and exposed to water and constant abrasion to remove the inert silicate, as could be achieved naturally by dumping olivine in the high energy surf of beaches. Experiments suggest that weathering process is reasonably quick given porous basalt rocks. Carbon dioxide naturally reacts with peridotite rock in surface exposures to ophiolites, notably in Oman. It has been suggested that this process can be enhanced to carry out natural mineralization of carbon dioxide. When carbon dioxide is dissolved in water and injected into the hot basaltic rocks underground, it has been shown that the carbon dioxide reacts with the basalt to form solid carbonate minerals. A test plant in Iceland started up in October 2017, extracting up to 50 tons of carbon dioxide a year from the atmosphere and storing it underground in basaltic rocks. Researchers from British Columbia developed a low-cost process for the production of magnesite, also known as magnesium carbonate, which can sequester carbon dioxide from the air, or at the point of air pollution, for example at a power plant. The crystals are naturally occurring, but accumulation is usually very slow. Demolition concrete waste or recycled crushed concrete are also potential low-cost minerals for mineral carbonation as they are calcium-rich waste material. Next is electrochemical method. Another method uses a liquid metal catalyst and an electrolyte liquid into which carbon dioxide is dissolved. The carbon dioxide then converts into solid flakes of carbon. This method is done at room temperature. Industrial use. Traditional cement manufacturers releases large amount of carbon dioxide, but newly developed cement type from Nevesem can absorb carbon dioxide from ambient air during hardening. A similar technique was pioneered by TechEco, which has been producing eco cement since 2002. A Canadian startup Carbon Cure takes capture carbon dioxide and injects into its concrete as it is being mixed. Carbon Upcycling UCLA is another company that uses carbon dioxide in concrete. Their concrete product is called concrete carbon dioxide, a concrete that hardens faster and is more eco-friendly than traditional concrete. In Estonia, oil shale ash generated by power stations could be used as a sorbent for carbon dioxide mineral sequestration. The amount of carbon dioxide captured averaged 60 to 65% of the carbonaceous carbon dioxide and 10 to 11% of the carbon dioxide captured. Chemical scrubbers. Various carbon dioxide scrubbing processes have been proposed to remove carbon dioxide from the air. usually using a variant of the Kraft process. Carbon dioxide scrubbing variant exists based on potassium carbonate, which can be used to create liquid fuels, or on sodium hydroxide. These notably include a artificial tree proposed by Klaus Lechner to remove carbon dioxide from the atmosphere using chemical scrubbers. Ocean-related basalt storage. Carbon dioxide sequestration in basalt involves the injecting of carbon dioxide into deep sea formation. The carbon dioxide first mixes with seawater and then reacts with the basalt, both of which are alkaline-rich elements. This reaction results in the release of calcium and magnesium ions, forming stable carbonate minerals. Underwater basalt offers a good alternative to other forms of oceanic carbon storage because it has a number of trapping measures to ensure adding protection against leakage. These measures include geochemical, sediments, gravitational, and hydrate formation. Because carbon dioxide hydrate is denser than carbon dioxide in seawater, the risk of leakage is minimal. Injecting the carbon dioxide at depths greater than 2,700 meters ensures that the carbon dioxide has a greater density than seawater, causing it to sink. One possible injection site is Jan and de Fuca Plate. Researchers at the Lamont Dehore Earth Observatory Foundation that this plate at the western coast of the United States has a possible storage capacity of 208 gigatons of carbon dioxide. This could cover the entire current United States carbon dioxide emission for over 100 years. This process is undergoing tests as a part of CRAP 6 project, resulting in 95% of the injected 250 tons of carbon dioxide to solidify into calcitate in 2 years using 25 tons of water per ton of carbon dioxide. Acid neutralization. Carbon dioxide forms carbonic acid when dissolved in water. So ocean acidification is a significant consequence of elevated carbon dioxide level and limits the rate at which it can be absorbed into the ocean. A variety of different bases have been suggested that could neutralize the acid and thus increase carbon dioxide absorption. For example, adding crushed limestone to ocean enhances the absorption of carbon dioxide. Another approach is to add sodium hydroxide to ocean, which is produced by electrolysis of salt water or brine, while eliminating the waste hydrochloric acid by reaction with the volcanic silicate rocks such as andesite, effectively increasing the rate of natural weathering of this rock to restore ocean pH. There are so many obstacles in the way of the carbon dioxide sequestration. Number one is the financial cost. This one is the major obstacle. The use of technology would add an additional 1 to 5% of cost per kilowatt hour. According to the estimate made by the Intergovernmental Panel on Climate Change, the financial cost of modern coal technology would nearly double if use of CCS technology were to be required by regulation. The cost of CCS technology differs with the different types of capture technology being used and with the different sites that it is implemented in. But the cost tends to increase with CCS capture implementation. One study conducted predicted that with new technologies these costs could be lowered but would remain slightly higher than prices without CCS technology. The second obstacle is the energy requirement. The energy requirement of sequestration process may be significant. In one paper, or according to one research, sequestration consumed 25% of the plant's rated 600 megawatt output capacity. Thank you.